Scene script. Have you ever pondered why statistics play such a pivotal role in the world of data science? Well, the answer lies in the very essence of data science itself. Think of data science as a ship sailing through a sea of raw, unstructured data. Now, statistics is the compass that guides this ship, helping it navigate through the complex waves of data. It provides the tools necessary to collect, analyze, and interpret data, turning it into valuable insights. When we collect data, we rely on statistical methods to ensure we're gathering a representative sample. When we analyze it, we use statistics to identify patterns, relationships, and trends. And when we interpret our findings, statistics helps us quantify uncertainty and make informed decisions. Moreover, statistics is the foundation of predictive modeling, a key aspect of data science. It empowers us to forecast future trends and behaviors based on past data. Statistics enables us to understand data in a more profound way and make informed decisions. The first step in understanding your data is through descriptive analysis. Delving into the world of data, descriptive analysis serves as our initial compass, guiding us through the vast landscape of information. This analytical approach helps us summarize and present data in a way that's digestible and meaningful. It's like painting a picture with numbers, where each stroke contributes to a comprehensive image of the data at hand. At the heart of descriptive analysis lie key concepts like means, medians, and standard deviations. The mean, often referred to as the average, is a central value that gives us a general idea of our data points. The median is the middle value that separates the higher half from the lower half of the dataset, providing a balanced perspective. Meanwhile, the standard deviation measures the dispersion or spread of data points, illustrating how much variation or diversity exists. By harnessing these tools, we piece together a clear, concise snapshot of our data. Descriptive analysis provides a clear snapshot of our data at hand. Now that we have a summary of our data, we can make inferences about a larger population. Welcome to the world of statistical inference, where we use data samples to make educated assumptions about a larger group. It's like being a detective, but with numbers. We gather clues from a small group and then we use those clues to make educated guesses about the larger population. One of the key tools in our statistical inference toolbox is constructing confidence intervals. These give us a range in which we expect a population parameter to fall based on our sample data. Imagine it as a safety net for our estimates. Then we have hypothesis testing. It's like a court trial for our data. We start with a null hypothesis that assumes no effect or relationship, and then we collect evidence from our data to see if we can reject this null hypothesis. Statistical inference allows us to make educated guesses about a larger population. To understand the relationships between variables and predict future outcomes, we turn to regression and probability. Regression, in its simplest form, is a statistical tool that allows us to study the relationship between two or more features. For instance, how does a person's age relate to their income? Or how does the temperature outside influence ice cream sales? Through linear regression, we can identify trends and use these to predict future outcomes. Nonlinear regression, on the other hand, allows us to model relationships that aren't as straightforward, where the rate of change isn't constant. This is particularly useful in more complex scenarios, like predicting the growth of a population. Now let's talk about probability. Probability is our mathematical way of dealing with uncertainty. It provides us with a framework for making sense of random phenomena. By assigning a likelihood to different outcomes, we can better understand and predict uncertain events. Regression and probability help us anticipate future trends and events. What if we can't study the entire population? That's where sampling comes into play. When we're dealing with large populations, it's often impractical, costly, or even impossible to collect data from every individual. So we use sampling, a technique where we select a subset of the population that accurately represents the whole. This sample becomes our mini version of the population, which we can study more easily and efficiently. Now let's imagine we've drawn our sample and we have a theory about our population. This theory is called a hypothesis. But how can we be sure this hypothesis holds water? That's where hypothesis testing comes in. It's a systematic way to test claims or ideas about a group or population. We analyze our sample data to see if it supports our hypothesis or not. Remember, data never lies, but it can mislead if not interpreted correctly. Sampling and hypothesis testing helps us to draw conclusions from smaller, more manageable data sets. And that's the magic of statistics. For more complex analyses involving multiple groups or variables, we turn to analysis of variance and multivariate statistics. Analysis of variance, often abbreviated as ANOVA, is a powerful statistical technique that allows us to compare the means of 3 or more groups. With this method, we can determine if there are statistically significant differences among the group means. It's like running multiple t-tests, but with a single comprehensive test that controls for the risk of false positives. On the other hand, multivariate statistics is a broad subfield of statistics encompassing techniques to analyze datasets with more than one variable. Specific methods under this umbrella can include factor analysis, which groups related variables together, or principal component analysis, which simplifies complex datasets by reducing the number of variables. These two techniques combined enable us to handle more complex datasets and analyses, giving us a deeper understanding of the relationships among variables and groups. These statistical techniques allow us to handle more complex datasets and analyses. Ever wondered how to incorporate prior knowledge into your analysis? Bayesian statistics is your answer. This statistical approach is like a seasoned detective, using previous information to solve new mysteries. In technical terms, it's about updating probabilities based on evidence. You start with a prior probability, which is your initial belief before seeing the data. Then you collect new data, and this leads you to an updated or posterior probability. Bayesian statistics allows us to continuously refine our predictions, much like how a detective revises their theories as new evidence comes to light. It's not just about the data you currently have, but also about what you already know and how that informs your analysis. It's a dynamic, ongoing process, always adapting and evolving. So if you're looking to bring a bit of Sherlock Holmes to your statistical analysis, Bayesian statistics is the way to go. Bayesian statistics allows us to refine our predictions based on prior knowledge and evidence. Now that we've explored these critical statistical concepts, let's revisit the role of statistics in data science. Statistics is the backbone of data science. It's the framework that allows us to extract insights from the vast sea of data. Each statistical concept we've discussed plays a pivotal role in the way we collect, analyze, interpret, and make decisions based on data. Descriptive analysis, for instance, helps us understand and summarize data using measures like means, medians, and standard deviations. It's like getting a bird's-eye view of the data landscape, giving us a clear picture of what we're dealing with. Statistical inference and hypothesis testing further extend our capacity to draw conclusions. They allow us to make educated guesses about a larger population based on a sample. And it's not just about making assumptions. It's about substantiating these assumptions with statistical evidence, testing hypotheses, and building confidence intervals. Regression analysis and probability studies help us understand relationships between variables and predict future events. These tools are invaluable in forecasting trends and modeling behaviors, supporting strategic decision-making in various fields from business to healthcare. The techniques of sampling ensure that we're working with representative data, while analysis of variance and multivariate statistics enable us to compare means and explore relationships among multiple variables. These techniques provide a more nuanced understanding of the data, revealing patterns and correlations that may otherwise go unnoticed. And finally, Bayesian statistics folds in our prior knowledge, updating probabilities based on new evidence. This iterative approach allows us to refine our models and predictions continually, making them more accurate and reliable over time. In essence, statistics equips us with the tools to navigate the complex world of data. It allows us to sift through noise, uncover patterns, make predictions, and ultimately make more informed decisions. It's not just about crunching numbers. It's about understanding what those numbers mean and how they can inform strategy and action. Having a solid understanding of statistics is essential to making the most out of data in data science. It allows us to make informed decisions and build predictive models.